Hi all, let's do some more graph theory proofs. So we'll start with a claim that's really just about vertices and edges. So here's the claim. In any simple graph G, remember simple means that edges only go between two vertices, right? You can't have an edge from a vertex to itself, and that between any two vertices we can only have one edge, not multiple. So in any simple graph G, the number of vertices with odd degree is even. So remember, degree is how many edges are incident to a vertex, right? So let's look at an example to start. Right, this vertex only connected to this edge, so it has degree 1. This vertex, right, 3 edges, so it has degree 3. And we could keep going. This also has degree 3, 3, 3, 3, 2, and 4. Okay. So what's our claim, right? The number of vertices with odd degree is even. And we can see that's true here, right? All 6 of these vertices have odd degree, and then these 2 have even degree, right? And 6 vertices of odd degree means we have an even number of vertices with odd degree. So this is just one graph, right? It was an example to get us started. We want to prove this is true for all simple graphs. So let's try that. Okay, so I'm going to say G has vertices, so I'm going to give some names just for convenience, V1 up through Vn. It doesn't really matter which one is which, this will just make it easier to write a particular statement later. And then we'll say that the number of edges G has is this. This is the size of the set of edges. Right, so this is some number. We could also say that this was K if we wanted. Okay. So if we think about, I'll draw a smaller graph this time. If we think about adding up the degree of all of the vertices, there's a relationship to the number of edges. So I'm sort of going to see what edges we count as we count degrees on this one. So let's start up here. This vertex has degree 2. We've looked at this edge and this edge. This vertex also has degree 2. Looking at this edge again, and this edge. This vertex has degree 3. We looked at these 2 edges for a second time, and this one for the first time. Sorry, that's a 3. And then that vertex has degree 1, and we look at that edge a second time. Right? If every edge is between exactly 2 vertices, then if we add up the degree of all of those vertices, right, all n vertices in the graph, we're going to get 2 times the number of edges, because we've counted each edge twice, once for each vertex at its end. But this is useful, right? This tells us that the sum of all the degrees of vertices in our graph has to be even. Remember, we want to know that the number of vertices with odd degree is even. So how does this help us, right? Well, remember, the sum of 2 even things is even, and the sum of 2 odd things is even. But the sum of an even and an odd number is odd. So if we want an even number for our degrees over here, we must end up with an even number of vertices of odd degree, right? Because if we don't, then we can think about so we have a bunch of even numbers, right? If we're summing the degrees. Right, we have a bunch of even numbers. They all sum to an even number. These are all the vertices with even degree, right? And now we're looking at the sum of odd numbers, the sum of the degrees of vertices with odd degree, right? We need this to also be even for us to get an even number at the end. But for a sum of odd numbers to be even, we must sum an even number of degrees. And that's exactly what we wanted to prove, right? Our number of vertices with odd degree must be even. So we're done.